9 billion years after the Big Bang, a cloud of gas and dust drifted through the galaxy. It was cold and silent. Then something changed. Gravity pulled it inward, crushing it tighter and tighter until, at its heart, heat and pressure ignited a new star. The Sun. Its light cut through the darkness. Its gravity seized everything around it. And from that moment, the solar system was born. The solar system is an enormous place. It's not just a collection of objects. It is a vast, structured domain shaped by the sun's power. It stretches far beyond what we can see, defined not by what's in it, but by the limits of the sun's reach. Everything within this space, from the smallest grain of dust to the largest storms of energy, moves under the rule of a single force: gravity. At its core, the sun burns with relentless energy, sending waves of light and radiation into space. Its pull keeps everything in motion, binding the solar system together. This influence extends across billions of miles, creating a system that is both dynamic and ever-changing. Our cosmic neighborhood includes 8 planets, around half a dozen dwarf planets, several hundred moons, and millions of asteroids and comets, all spinning around the sun, and in many cases each other at speeds of thousands of miles per hour, like a giant top. But where does it end? The true boundary of the solar system is not a line, but a fading force. The sun's gravity stretches indefinitely, but its solar wind, an unceasing stream of charged particles, creates a bubble around it, known as the Heliosphere. This invisible shield reaches about 11 billion miles from the sun. Here, solar wind meets the vast, unfiltered radiation of interstellar space, marking the final breath of the sun's influence. Beyond the heliosphere, the solar system slowly dissolves into the galaxy. The sun's pull weakens, and its presence fades into the cosmic background. But within this enormous space, everything still belongs to the solar system. A system defined not by its individual parts, but by the reach of its central star. This is the solar system, a kingdom of light, gravity, and motion, carved into the fabric of space by a single burning star. Let's start our journey from the center of the system, the heart of everything, the sun. A blazing sphere of nuclear fire, a cosmic engine burning with relentless energy. It is ancient, powerful, and utterly dominant, holding the solar system together with an invisible force. The sun is 4.6 billion years old, formed from the same swirling cloud of gas and dust that created everything around it. It is a giant compared to anything else in the solar system, making up 99.8% of all the mass in our cosmic neighborhood. If you could gather everything, every planet, moon, asteroid, and comet, and pile them together, they would still be nothing compared to the sheer bulk of the sun. It stretches around an 866,000 mile across, more than 109 times wider than Earth. Over 1 million Earths could fit inside it. And yet, despite its overwhelming size, it is just an ordinary star, one of billions in the galaxy. But how did it come to be? To understand the Sun, we have to go back billions of years to the cold, dark past before its light first touched space. The Sun was born in the chaos of a collapsing nebula, a vast cloud of hydrogen and helium left over from generations of dead stars. For millions of years, this cloud drifted in space, shapeless and still. Then something triggered its collapse, perhaps the shockwave of a distant supernova. Gravity took over, pulling the gas inward, compressing it tighter and tighter. As the cloud shrank, it began to spin, flattening into a swirling disk. At the center of this chaos, heat and pressure built up until hydrogen atoms were forced together, fusing into helium. This moment, nuclear fusion, was the birth of the Sun. A sudden burst of energy erupted outward, a brilliant fire igniting at the heart of the forming solar system. The newborn Sun blasted away the remaining gas with powerful solar winds, shaping the planets and everything that now orbits it. But the Sun is more than just a burning ball of gas. It is the force that rules the solar system. Its gravity extends for billions of miles, a pull so strong that nothing within its reach can escape. Every planet, every asteroid, every frozen body in the distant edges of the system obeys its command. If the Sun were to vanish, the entire solar system would dissolve into chaos, its planets flung into the void. Gravity is what makes the solar system a system. The Sun's mass bends space itself, creating an invisible web that holds everything in place. This force is why Earth takes 365 days to complete its orbit, why Mercury races around the Sun in just 88 days, and why distant Neptune takes a slow 165 years. Even Pluto and beyond feel its pull, their orbits stretching across centuries. The Sun's influence doesn't stop with its gravity. It is constantly releasing energy, flooding the solar system with heat and light. Without this energy, Earth would be a frozen wasteland. Mars would never have had a chance for liquid water, and the outer planets would exist in total darkness. It is a cosmic furnace, burning through 600 million tons of hydrogen every second, a process that will continue for another 5 billion years. But the Sun is not peaceful. Its surface is a boiling sea of plasma, constantly shifting, erupting with massive flares and solar storms. Gigantic loops of charged particles, known as prominences, stretch thousands of kilometers into space, sometimes collapsing in violent explosions. These storms can send blasts of radiation hurtling toward Earth, disrupting satellites, radio signals, and even power grids. And yet, despite its fury, the Sun is stable, steady enough to support life, yet active enough to remind us of its raw power. Its light takes just 8 minutes and 20 seconds to reach Earth, traveling at 186,000 miles per second. This light carries more than just warmth. It carries the energy that drives our climate, fuels plants, and makes life possible. Without the Sun, Earth would be a lifeless rock, drifting in frozen silence. And yet, despite all its power, the Sun is just one star. It sits in the outer region of the Milky Way, moving at 515,000 miles per hour, dragging the entire solar system along with it as it orbits the galactic center. In 230 million years, it will complete one full trip around the galaxy, a journey it has made more than 20 times since it was born. But for now, we stay close, watching from within its reach. And as we move away from this blazing giant, we find the first world caught in its grasp. A small, scorched planet, locked in an eternal battle with the sun's heat. Next, we arrive at Mercury. Mercury, the first planet from the Sun, is a world of extremes. It is the smallest planet in the solar system, barely larger than Earth's moon, yet it endures some of the most intense conditions found anywhere. Locked in a delicate dance with the Sun, Mercury is a scorched, airless rock, bombarded by solar radiation and whipped by temperature swings that defy imagination. Despite being the closest planet to the Sun, Mercury is not the hottest. That title belongs to Venus, but that doesn't make Mercury any less brutal. During the day, the Sun dominates its sky, heating the surface to 800 degrees Fahrenheit, hot enough to melt lead. But with no atmosphere to trap the heat, the temperature plunges at night, falling to negative 290 degrees Fahrenheit, a shift of over 1,000 degrees in a single rotation. A day on Mercury is unlike anything we experience on Earth. The planet has a slow rotation, taking 59 Earth days to spin once on its axis. But because of its fast orbit around the Sun, just 88 Earth days, a single day-night cycle on Mercury lasts 176 Earth days. If you stood on its surface, you would see the Sun rise, slow to a stop, move backward briefly, then continue forward again, creating one of the strangest skies in the solar system. Mercury's surface is a battered landscape of craters and cliffs shaped by billions of years of impacts. The planet has no wind, no rain, and no geological activity to erase the scars of its past. One of its most famous features is Heliosphere Basin, a massive impact crater over 1,000 miles wide, so large it could stretch across much of the United States. When the asteroid that created it struck Mercury, the force was so great that it sent shockwaves across the entire planet, creating strange, hilly formations on the opposite side. Mercury's isolation and harsh conditions make it one of the least explored planets. Only 2 spacecraft have ever visited it. NASA's Mariner 10, which flew by 3 times in the 1970s, and Messenger, which orbited Mercury from 2011 to 2015. Messenger gave us our best look at the planet, mapping its surface in detail, measuring its gravity and magnetic field, and even confirming the presence of those polar ice deposits. But Mercury is just the beginning. As we leave behind this small, sun-scorched world, we move outward toward a planet wrapped in thick, golden clouds. A world even more hostile than Mercury, where the heat never fades and the air itself is poison. Ahead of us, a new world emerges. Welcome to Venus, the second planet from the Sun and the most extreme of the inner planets. At first glance, it might seem like Earth's twin, It's nearly the same size, with a similar rocky composition. But beneath its thick, golden clouds lies a world that couldn't be more different. Venus is the hottest planet in the solar system, with surface temperatures reaching 900 degrees Fahrenheit. Unlike Mercury, which cools down at night, Venus never gets a break. Its thick atmosphere, made mostly of carbon dioxide, traps heat in a runaway greenhouse effect, turning the entire planet into a suffocating oven. This atmosphere is so dense that standing on Venus would feel like being a kilometer underwater on Earth. And the air itself, it's filled with sulfuric acid clouds, making Venus not just hot, but corrosive and deadly. But Venus has another strange feature: its rotation. It spins backward compared to most planets, with the sun rising in the west and setting in the east, and it does so incredibly slowly. A single Venusian day lasts 243 Earth days, which is actually longer than its year, since it only takes 225 Earth days to orbit the Sun. That means if you lived on Venus, a full day would last nearly an entire year. Venus has no large moons, no protective magnetic field, and no plate tectonics like Earth. Instead, its entire surface seems to behave like a single giant plate, with heat from the planet's interior occasionally building up and causing catastrophic resurfacing events. Without tectonic plates to slowly release that heat, Venus may go through long periods of relative calm, followed by planet-wide volcanic upheavals that remake the entire surface. That could explain why Venus's crust is so much younger than Earth's. Despite the hellish conditions on the surface, there's been speculation that life, or at least something like it, could survive high in Venus's atmosphere. About 50 kilometers above the surface, temperatures and pressures are surprisingly Earth-like, and there are even trace amounts of water vapor. In 2020, scientists announced the detection of phosphine, a gas that on Earth is mostly produced by microbes in Venus's upper atmosphere. The discovery sparked debate about whether some form of airborne microbial life could exist in the planet's clouds. However, follow-up studies have cast doubt on the phosphine detection, and the question of whether life ever existed on Venus remains open. Pushing further into the solar system, we reach the Earth, a planet unlike any other. From space, it appears as a shimmering blue jewel, wrapped in swirling white clouds. It is 4.54 billion years old, born from the same cosmic dust that created the Sun and the other planets. Yet, unlike its neighbors, Earth became something extraordinary. It is a world of rock and metal, its core an iron heart generating a protective magnetic field. Its surface, ever-changing, is sculpted by oceans, winds, and shifting tectonic plates. Features that have shaped mountains, carved valleys, and given rise to continents that drift over time. Unlike Venus, whose thick atmosphere suffocates the planet, or Mars, whose air is almost non-existent, Earth's atmosphere is just right, a delicate balance of nitrogen and oxygen, creating a thin, life-sustaining envelope that separates it from the cold vacuum of space. But Earth, for all its stability now, was once a violent world. In its infancy, it was a molten sphere, constantly bombarded by asteroids and comets. Over millions of years, its surface cooled, forming a solid crust. Water, delivered by icy comets or released from within, pooled into vast oceans. Volcanoes reshaped the land, and the atmosphere thickened, setting the stage for something that no other known world has achieved: life. From above, Earth pulses with motion, oceans churn with currents, clouds shift in endless patterns, and lights flicker across the dark side as civilizations illuminate the night. It is the only planet known to host life, not because it is the only one capable, but because here, the conditions aligned perfectly. The habitable zone, the narrow band around a star where conditions allow liquid water to exist, is part of why Earth is so special. But location isn't everything. Venus is in the habitable zone too, yet it's a scorched wasteland. Earth's long-term habitability depends on many factors: its magnetic field, plate tectonics, atmosphere, oceans, and perhaps even the presence of the Moon. Earth's only natural satellite is far more than just a pretty light in the night sky. It plays a crucial role in Earth's story. Formed in a colossal impact between Earth and a Mars-sized body called Theia, the Moon's gravitational pull helps stabilize Earth's tilt. Without the Moon, Earth's axis might wobble wildly, causing chaotic climate swings that could make life impossible. The Moon also drives tides, stirring ocean waters and influencing everything from coastal ecosystems to global weather patterns. Leaving our home planet, our next destination is our potential future home: the red planet, Mars. Mars has been a source of curiosity for thousands of years. It's visible to the naked eye from Earth, glowing with a distinctive reddish hue that made ancient civilizations associate it with war and fire. But the real Mars, the Mars we've come to know through decades of robotic missions, is both stranger and more fascinating than any myth. It's a planet of extremes, a frozen desert with vast canyons, towering volcanoes, and signs that water once flowed across its surface. Yet today, it's dry, cold, and seemingly lifeless. A reminder of how quickly a planet's fate can change. Mars orbits the Sun at an average distance of 1.52 astronomical units, meaning it's about 141 million miles or 227 million kilometers away, farther than Earth, but still relatively close in cosmic terms. In fact, Mars was the first planet whose distance was measured using astronomical units. Since astronomical units is based on Earth's average distance from the Sun, measuring Mars's orbit helped early astronomers refine their understanding of the solar system's scale. It's smaller than Earth, just over half the size, and with only a third of the gravity, you'd feel almost weightless compared to our planet. But don't be fooled by its familiar landscapes. Mars is a harsh, unforgiving place, a world where temperatures plunge far below freezing and the air itself is unbreathable. From space, it glows a deep red thanks to iron-rich dust coating its surface. This fine, powdery layer stretches across endless deserts, shaped by fierce winds that can stir up storms covering the entire planet for months. But there's more to Mars than just dust. Towering above the landscape is Olympus Mons, the tallest volcano in the entire solar system. It rises 3 times higher than Mount Everest, a frozen giant from an era when Mars was alive with fire. And then there's Valles Marineris, a canyon system so vast it would stretch across the entire United States. If Earth's Grand Canyon is a scar, Valles Marineris is a deep, jagged wound carved into the Martian surface. But for all its extremes, Mars holds secrets that make it one of the most exciting places in the solar system. Billions of years ago, it was different. We know that water once flowed here. Long, winding riverbeds, dried up lake basins, and even what might have been a massive ocean covering the northern half of the planet. Today, water still exists, but only as ice, locked away beneath the surface and at the poles. And where there was water, could there have been life? That's the big question. Rovers like Curiosity and Perseverance have been scouring the planet, looking for signs that life might have existed in Mars's past, or maybe even still hides underground. Mars's atmosphere is another mystery. It's incredibly thin, made mostly of carbon dioxide, and offers almost no protection from the sun's radiation. If you stood on the surface without a suit, the lack of pressure would make your blood boil in seconds. And because there's so little atmosphere to hold in heat, temperatures swing wildly, warm enough in the daytime to make you think it's almost Earth-like, then plunging to deadly cold at night. Mars is a planet of extremes, a place where survival would be nearly impossible without technology. It has 2 tiny moons, Phobos and Deimos, small, lumpy, and likely captured asteroids. Phobos, the larger one, is slowly being pulled toward Mars and will one day crash into the planet or break apart, forming a thin ring. Deimos, on the other hand, drifts lazily in a distant orbit, a tiny rock lost in the vast Martian sky. For centuries, Mars has been the focus of human curiosity, the most Earth-like planet we've ever found, yet so incredibly different. It's also the most likely place for us to set foot next. Plans for human missions are already in motion, with NASA, SpaceX, and other space agencies looking at ways to send astronauts to Mars in the next few decades. It won't be easy, but if we can land there, survive, and maybe even build a base, Mars could become the first step in making humanity a multi-planet species. Mars is also the last of its kind, the final rocky world in the inner solar system. But before we reach the next planet, we must cross a vast boundary into something completely different: the Asteroid Belt. This region stretches from about 2.1 to 3.3 astronomical units from the Sun, or roughly 186 million to 370 million miles. This isn't a single structure, but a chaotic, scattered ring of millions of rocky objects drifting in endless orbits. It marks the dividing line between the inner rocky planets and the gas giants beyond, a boundary between 2 entirely different realms of the solar system. Despite its name, the asteroid belt is not a tightly packed field of tumbling boulders. If you were standing on an asteroid, you'd likely see nothing but empty space. The distance between objects can be hundreds of thousands of miles, making navigation through it far less hazardous than science fiction would suggest. But make no mistake, these asteroids are relics of the solar system's birth. remnants of a failed planet that never formed due to the immense gravitational pull of nearby Jupiter. The largest object here is Ceres, a dwarf planet with a diameter of 590 miles, making up about 40% of the asteroid belt's total mass. Unlike its rocky neighbors, Ceres has large amounts of water ice beneath its surface, and recent studies suggest it may even have a slushy, salt-rich ocean deep below. If there's any possibility of life in this region, Ceres is where it might be hiding. Next in size are Vesta, Pallas, and Hygiea, each several hundred miles wide. Vesta is the second largest, with a surface scarred by ancient impacts and deep fractures. It's one of the few places in the belt where volcanic activity may have once occurred. Some asteroids like Ida and Dactyl even have their own tiny moons, held in weak orbits by gravity. Others like Eros and Itokawa are nothing more than rubble piles, collections of loose rocks barely clinging together. While most asteroids remain in stable orbits, some get nudged by gravitational forces, especially from Jupiter, which dominates this region of space. These displaced asteroids, known as near-Earth objects, occasionally cross Earth's orbit. Some, like the one that wiped out the dinosaurs 66 million years ago, have altered the course of life on our planet. Today, space agencies track these rogue asteroids carefully, preparing for the possibility that one might threaten Earth again. But the asteroid belt is also a potential stepping stone for the future. Many asteroids are rich in iron, nickel, and platinum group metals, materials that could one day fuel human expansion into space. Some companies and space agencies have even considered mining these asteroids, extracting water for rocket fuel, and using their resources to build future space stations. As we drift past the last scattered fragments of this ancient region, ahead of us looms the first of the outer planets, a world so massive that it could swallow every other planet and still have room to spare. Now, we arrive at Jupiter. This giant planet is impossible to ignore. It dominates the outer solar system, a behemoth of swirling gas and violent storms, the king of planets. If the solar system had a second sun that never ignited, it would be this. Jupiter holds 318 times the mass of Earth, more than twice the mass of all other planets combined. It's a world so immense that its gravity shapes the orbits of comets, tugs at asteroids, and even influences its planetary neighbors. If not for Jupiter, the solar system would look completely different. It sits at 5.2 astronomical units from the Sun, about 484 million miles away. A world of churning clouds, Jupiter has no solid surface. Instead, it's a thick atmosphere consisting of mainly a hydrogen and 10% of helium, much like the Sun itself. Deeper down, the pressure crushes gas into liquid metallic hydrogen, a substance so bizarre that it behaves like an electrical conductor, creating Jupiter's mighty magnetic field. Beneath that, a dense core lurks, though scientists still debate its exact size and composition. Jupiter's most famous feature is the Great Red Spot, an enormous storm that has raged for at least 350 years. It's a swirling vortex twice the size of Earth, with wind speeds of 400 miles per hour, an unrelenting hurricane that never dies. Surrounding it, Jupiter's atmosphere is streaked with bands of color, white, orange, brown, created by jet streams moving in opposite directions at incredible speeds. These bands, called zones and belts, are made of ammonia clouds stretched across the entire planet by its rapid rotation. Jupiter spins faster than any other planet, completing a full day in just 9 hours and 56 minutes. That rotation fuels violent storms, chaotic winds, and towering cloud formations that reach 30 miles high. Beneath the storms lies an ocean of metallic hydrogen, covering most of the planet's interior. This strange liquid conducts electricity, fueling a magnetic field 20,000 times stronger than Earth's. It extends millions of miles into space, trapping charged particles and creating intense radiation belts. Any spacecraft that gets too close risks being fried by radiation stronger than the worst nuclear reactor meltdown. Even Jupiter's own moons have been scarred by this relentless energy. And then there's the gravity. Jupiter's mass warps space around it, pulling in comets and asteroids like a cosmic vacuum cleaner. It has deflected some space debris away from Earth, acting as a protector, but it has also redirected others toward us, sending some on collision courses that shaped our planet's history. Its influence extends far beyond its size. Jupiter's gravity prevents the asteroid belt from forming into a planet, and it has even captured its own set of 95 known moons. Among them, the 4 largest, Io, Europa, Ganymede, and Callisto, the Galilean moons, are worlds of their own, each more interesting than some planets. Io is the most volcanically active body in the solar system, its surface constantly reshaped by sulfur-spewing geysers. Europa hides a vast underground ocean that might harbor life. Ganymede is the largest moon in the solar system, even bigger than Mercury, and has its own magnetic field. Callisto, a battered and ancient ice world, might have a buried ocean too. Moving out from Jupiter, our next destination is Saturn. Saturn is the jewel of the solar system. A world wrapped in golden light, encircled by rings so vast they could stretch almost from Earth to the Moon. If Jupiter is the king, Saturn is the elegant ruler, quieter, colder, but no less powerful. It sits at 9.5 astronomical units from the Sun, about 886 million miles away. Though it's the second largest planet, it's strangely light for its size. If you could place Saturn in a bathtub big enough to hold it, it would float. That's because it's mostly hydrogen and helium, the least dense planet in the solar system. Like Jupiter, Saturn has no solid surface, just endless clouds of ammonia and methane, swirling in bands of pale yellow, gold, and cream. But beneath those soft colors is a stormy world. Winds on Saturn reach 1,100 miles per hour, nearly 3 times the speed of a Category 5 hurricane. Near the North Pole, an immense, perfectly shaped hexagonal storm spans 20,000 miles across, its strange symmetry still baffling scientists. Saturn's deep interior is much like Jupiter's, with crushing pressures turning hydrogen into an exotic metallic form, generating a strong but less intense magnetic field. But it's the rings that steal the spotlight. Stretching 175,000 miles across, yet only about 30 feet, about 10 meters, thick. They are made of countless ice and rock fragments, some as small as grains of sand, others the size of mountains. These rings aren't solid, but a vast, constantly shifting collection of debris. Divided into 7 main sections, A to G, each section has its own unique characteristics, shaped by the planet's gravity and the constant tug of its moons. The A and B rings are the brightest and most massive, densely packed with ice chunks that reflect sunlight brilliantly. The C ring is fainter and more translucent, contains finer particles, giving it a ghostly, almost transparent appearance. Beyond these main rings, the D ring, closest to Saturn, is so thin and diffuse that it's barely visible. Moving outward, the E ring is vast and diffuse, created by the icy plumes erupting from the moon Enceladus, while the F ring is a narrow, chaotic band constantly twisted and reshaped by nearby moonlets. And finally, the G ring, the faintest of all, drifts at the edge of Saturn's influence, a thin whisper of material barely holding together. But what's perhaps most fascinating is the Cassini division, the dark gap between the A and B rings. It's not empty, it still holds scattered particles, but its 2,920-mile wide span is largely cleared out by the gravitational pull of the tiny moon Mimas, which orbits nearby. This division, along with many smaller gaps, shows how Saturn's moons act as celestial sculptors, shaping and maintaining the delicate balance of the rings. These moons, some embedded within the rings, others orbiting just outside, shepherd the ice and rock, keeping some areas clear while causing waves and ripples elsewhere. And Saturn has a lot of moons, at least 146 known so far. Some are tiny, barely large enough to be called moons at all, while others are worlds in their own right. The most famous is Titan, larger than Mercury, with a thick atmosphere of nitrogen and methane. Titan is the only place in the solar system besides Earth where liquid lakes and rivers exist, though they are made of liquid methane instead of water. Another, Enceladus, hides an ocean beneath its icy shell, spraying geysers of water into space, one of the best places to search for life. Despite its serene appearance, Saturn's gravity is a force to be reckoned with. It exerts 95 times the mass of Earth, holding its rings, moons, and even influencing distant objects in the solar system. Some asteroids and comets that pass through Saturn's domain are nudged into new orbits, sometimes flung into deep space, sometimes sent tumbling toward the inner solar system. As we drift away, leaving behind the golden glow and icy rings, we approach a planet darker, stranger, and full of secrets. Next, we arrive at Uranus. Uranus, a world unlike any other. It sits at 9.8 astronomical units from the Sun, nearly 1.8 billion miles away. It's the 7th planet, an ice giant, wrapped in a cold, hazy atmosphere that hides its mysteries beneath. Unlike its larger neighbors, Jupiter and Saturn, Uranus doesn't shine with swirling storms or towering cloud bands. Instead, it appears as a smooth, featureless blue-green sphere, its color coming from methane in the atmosphere, which absorbs red light and reflects blue. But the most bizarre thing about Uranus isn't its color, it's the way it moves. Unlike every other planet, which spins more or less upright, Uranus is tipped over on its side, rotating at a 98-degree tilt. That means instead of spinning like a top, it rolls around the Sun like a ball. Astronomers believe this strange tilt was caused by a massive collision billions of years ago, possibly with a planet-sized object that knocked Uranus over. As a result, the planet experiences some of the most extreme seasons in the solar system. For nearly 42 years, one pole faces the Sun in constant daylight while the other is trapped in total darkness. Then, as Uranus orbits, the situation reverses. At 4 times wider than Earth, Uranus is mostly made of hydrogen, helium, and methane. But deep inside, it's very different from a gas giant like Jupiter. Beneath its atmosphere lies an icy, slushy interior of water, ammonia, and methane, surrounding a small, rocky core. This is why Uranus and Neptune are called ice giants. They contain much more ice than gas. And even though Uranus looks calm, it's not. The planet has some of the fastest winds in the solar system, reaching 560 miles per hour. Like Saturn, Uranus has rings, but they are thin, dark, and faint, nearly invisible except when backlit by the Sun. It also has 27 known moons, many named after characters from Shakespeare and Alexander Pope. The largest, Titania and Oberon, are icy, cratered worlds, while others, like Miranda, have strange, fractured landscapes that hint at violent pasts. As we drift past this sideways world, we set our sights on the last great planet of the solar system, Neptune. Neptune, the 8th and final planet in the solar system. Sitting at an incredible 30.1 astronomical units from the Sun. That's 2.8 billion miles away. Neptune is a world of deep blue mystery. It's a true ice giant, similar to Uranus, but wilder, more dynamic, and filled with raging storms. Despite being so far from the Sun, where sunlight is 900 times weaker than on Earth, Neptune is anything but calm. Its deep blue color, richer than Uranus's, comes from methane in the atmosphere, which absorbs red light and scatters blue. But this serene appearance is deceiving. Neptune is home to the fastest winds in the solar system, reaching 1,200 miles per hour. That's faster than the speed of sound on Earth. These winds whip through its thick hydrogen, helium, and methane atmosphere, stirring up massive storms. The most famous of these was the Great Dark Spot, a storm similar to Jupiter's Great Red Spot, first seen by Voyager 2 in 1989. Though it later disappeared, other dark storms have since formed, proving that Neptune's weather is ever-changing. Beneath those stormy clouds, Neptune's atmosphere gradually thickens into a hot, dense fluid of water, ammonia, and methane. This slushy, supercritical layer is similar to what's found inside Uranus, but Neptune's more intense internal heat may make it more active. Deeper still, there's likely a small rocky core, about 1.2 times Earth's mass, surrounded by a mantle of hot ices and liquids under extreme pressure. Temperatures in Neptune's deep interior could reach 5,000 degrees Celsius, about 9,000 degrees Fahrenheit, hot enough to melt even rock. That deep interior might hold one of the solar system's strangest phenomena, diamond rain. The pressures inside Neptune are so intense that carbon atoms could be squeezed into diamond crystals, which would then fall like glittering rain toward the core. This isn't just a wild theory. Lab experiments on Earth have recreated the conditions that could trigger diamond formation in Neptune-like environments. If true, Neptune's hidden depths could be filled with sinking diamonds, adding to the eerie beauty of this distant world. Neptune also has a system of faint, thin rings, likely made of dust and ice, constantly reshaped by its 14 known moons. The largest, Triton, is one of the strangest moons in the solar system. It orbits Neptune backward, meaning it was likely captured from the Kuiper Belt, a distant region of icy objects beyond Neptune. Triton is also the coldest known body in the solar system, with surface temperatures plunging to -235 degrees Celsius. Yet despite this extreme cold, it's still geologically active, with geysers of nitrogen gas erupting from beneath its frozen surface. Neptune itself was the first planet discovered not by direct observation, but by mathematics. In the early 1800s, astronomers noticed that Uranus's orbit wasn't quite following predictions. Something was tugging at it. Using the laws of gravity, astronomers calculated the position of a hidden planet. And in 1846, Neptune was found almost exactly where they predicted. That discovery showed that the solar system was still full of surprises, even at the edge. Despite its incredible distance, Neptune isn't entirely cut off from the Sun's influence. The solar wind still reaches this far, though it's weak and stretched thin by the time it gets to Neptune's magnetosphere. The Sun's gravity also keeps Neptune locked in a resonance with Pluto. For every 3 orbits Neptune completes, Pluto completes 2, ensuring they never come too close to each other despite their overlapping paths. Beyond Neptune, the solar system doesn't just stop. It stretches into a vast, frozen expanse called the Kuiper Belt. This is a distant, icy region where the Sun looks like just another bright star in the sky. It starts about 30 astronomical units from the Sun. That's 30 times the distance between Earth and the Sun, and extends out to roughly 55 astronomical units. That's over 5 billion miles away. Out here, space isn't empty. It's filled with countless icy objects, leftovers from the formation of the solar system. Some are tiny, no bigger than a rock. Others are the size of mountains. And then there are the dwarf planets, the largest and most famous objects of this region. For decades, Pluto was considered the 9th planet, a lonely little world at the edge of the solar system. But in 2006, astronomers made a tough decision. They redefined what it means to be a planet, and Pluto didn't make the cut. The problem wasn't its size. After all, Mercury is smaller than some moons and still counts as a planet. The issue was its orbit. A real planet, by definition, needs to dominate its path around the Sun. Pluto doesn't. It shares its orbit with many other objects in the Kuiper Belt, meaning it's just one of many icy worlds out here. So Pluto got reclassified as a dwarf planet, joining a growing list of similar worlds like Eris, Haumea, and Makemake. Even though it's no longer a planet, Pluto is still one of the most fascinating places in the solar system. It's covered in frozen nitrogen, methane, and carbon monoxide, and has a thin atmosphere that collapses and refreezes onto the surface as it moves farther from the Sun. In 2015, NASA's New Horizons spacecraft flew past Pluto for the first time, revealing a landscape unlike anything we expected. Towering ice mountains, vast smooth plains, and signs of possible underground oceans. It's a place where the surface shifts and changes, proving that even a world so far away from the Sun can still be alive in its own way. But Pluto isn't the only large object out here. There are other dwarf planets, each with their own mysteries. Haumea is one of the weirdest objects in the Kuiper Belt. It spins so fast that it's been stretched into an elongated, almost egg-like shape. It also has rings, making it one of the few known ringed objects beyond the gas giants. Then there's Makemake, which is covered in frozen methane, giving it a reddish hue. Its surface is so cold that even gases like nitrogen and methane freeze solid, forming a thin, patchy layer of ice. But these are just the big names. The Kuiper Belt is full of thousands, maybe even millions, of smaller icy objects that have never been explored. Some may be tiny, just chunks of frozen rock, but others could be undiscovered dwarf planets waiting in the darkness. Many of these objects follow strange, elongated orbits shaped by the gravity of Neptune, and possibly even an unseen planet lurking beyond the Kuiper Belt. The Kuiper Belt is also the source of many short-period comets, the ones that orbit the Sun in less than 200 years. Every once in a while, the gravity of Neptune nudges one of these icy bodies inward, sending it on a journey toward the inner solar system. When that happens, the Sun's heat causes the comet to release gas and dust, creating the bright, glowing tail we see from Earth. One of the most famous comets, Halley's Comet, is thought to come from this region. But the Kuiper Belt isn't the final boundary of the solar system. As we move farther out, the objects become more scattered, drifting into a chaotic region known as the scattered disk. The scattered disk is the place where the solar system starts to unravel. If the planets and the Kuiper Belt are the well-maintained garden close to the house, the scattered disk is the overgrown field at the far end of the property. A wild, messy place where gravity and chance have left objects stranded in erratic orbits. It begins around the outer edge of the Kuiper Belt, roughly 30 astronomical units from the Sun, and extends far beyond, out to at least 1,000 astronomical units, though the exact boundary isn't clean-cut. But unlike the relatively stable objects of the Kuiper Belt, the scattered disk is home to icy bodies with extreme orbits, some tilted at sharp angles, others stretched into long elliptical paths that carry them far from the Sun, before swinging back in again. These objects didn't form this way. They were once part of the Kuiper Belt. But long ago, Neptune's immense gravity disrupted them, flinging them into these eccentric, unpredictable trajectories. One of the most famous scattered disk objects is Eris, a dwarf planet that is slightly smaller than Pluto, but far more massive. Eris orbits the Sun at an average distance of 68 astronomical units, but its path is highly elongated, taking it as far as 97 astronomical units, and as close as 38 astronomical units. Just in case you forgot, 1 astronomical unit is the average distance between the Earth and the Sun, about 93 million miles. That means Eris, even at its closest, is nearly 40 times farther from the Sun than Earth, and at its farthest, it's nearly 100 times that distance, making it one of the most remote known objects in the solar system. Its orbit is also tilted 44 degrees compared to the plane of the solar system, a telltale sign that it was tossed there by Neptune long ago. In 2005, when Eris was first discovered, it was initially thought to be larger than Pluto, sparking the debate that ultimately led to Pluto's reclassification as a dwarf planet. Eris isn't alone. There are many other known scattered disk objects, including Gong, Sedna, and 2007 OR10, some of which may also qualify as dwarf planets. Most of these objects have never been seen up close. We only know them as tiny points of light, their surfaces completely unknown. But what we do know is that they are among the reddest objects in the solar system, likely covered in complex organic molecules formed from radiation bombarding their icy surfaces. The scattered disk is different from the Kuiper Belt in one key way. It isn't really a belt at all. The Kuiper Belt is a relatively flat region, following the same general plane as the planets. But the scattered disk is all over the place. Some of its objects have orbits that stretch high above or far below the plane of the solar system, tilted at extreme angles. This suggests that these objects didn't just get nudged by Neptune, they were flung, violently tossed into their current orbits. In fact, some of them may have been sent so far out that they became part of the next region. One of the most intriguing objects in the scattered disk is Sedna, a reddish world that never comes closer than 76 astronomical units to the Sun, and swings out as far as 937 astronomical units, far beyond the reach of Neptune's gravity. Its orbit takes about 11,400 years to complete, meaning it was last in its current position when humans were still painting on cave walls. The reason for Sedna's bizarre orbit is a mystery. Some scientists believe it was pulled into its current path by a passing star in the Sun's infancy. Others think it might have been influenced by an unseen planet lurking far beyond Neptune, what some call Planet 9, a hypothetical world that could be hiding in the darkness. Far beyond the scattered disk, past the last known dwarf planets and the reach of Neptune's gravitational influence, the solar system begins to dissolve into the vast emptiness of interstellar space. But it doesn't end abruptly. Instead, it fades into a distant, invisible shell of icy objects, a place so far from the Sun that even its mighty gravity barely holds on. This is the Oort Cloud, a vast, mysterious region believed to be the last frontier of the solar system. The Oort Cloud is unlike anything we've encountered so far. It isn't a flat disk like the Kuiper Belt, or a chaotic scattering of ice and rock like the scattered disk. Instead, it forms a vast sphere surrounding the Sun from all directions, stretching from around 2,000 astronomical units to as far as 100,000 astronomical units. That means the Oort Cloud's outer edge could be as much as 9.3 trillion miles away. Light from the Sun would take over a year to reach the outer edge of the Oort Cloud. Unlike the inner solar system, where planets and asteroids orbit in relatively neat, predictable paths, the objects in the Oort Cloud are spread in all directions, moving slowly in the darkness. No spacecraft has ever traveled far enough to see them up close. In fact, we've never directly observed an Oort Cloud object. We only know it exists because of the long-period comets, icy bodies that fall toward the Sun from extreme distances before swinging back out into the unknown. Some of these comets take thousands or even millions of years to complete a single orbit, hinting at an origin far beyond the Kuiper Belt or scattered disk. Scientists believe the Oort Cloud is made up of trillions of icy bodies, leftovers from the formation of the solar system. These objects were likely born much closer to the Sun, in the same swirling disk of dust and gas that formed the planets. But in the early days of the solar system, they were thrown outward by the immense gravity of Jupiter and the other giant planets, flung so far that they settled into this vast, distant shell. Some may have even come from other star systems, captured by the Sun's gravity billions of years ago. One of the biggest mysteries of the Oort Cloud is just how far it extends. Its inner edge, at around 2,000 astronomical units, about 186 billion miles, is still loosely bound to the Sun. But at its outermost limits, around 100,000 astronomical units, 9.3 trillion miles, the Sun's gravity is barely stronger than the pull of passing stars, or the faint tug of the Milky Way itself. Some scientists even suspect there could be a second, even more distant shell of icy bodies called the Oort Cloud, extending the solar system's reach even farther. Comets are our best evidence of the Oort Cloud's existence. When a distant Oort Cloud object is disturbed, perhaps by the gravitational pull of a passing star, it can begin a slow, spiraling fall toward the inner solar system. As it gets closer to the Sun, its icy surface starts to vaporize, forming the bright tails that make comets so spectacular. Perhaps the most fascinating question about the Oort Cloud is whether it holds undiscovered worlds. Most of its objects are small, just a few miles across. But some scientists believe there could be larger bodies hiding in its depths. Perhaps even a Mars-sized planet that was ejected long ago and now drifts through the darkness, frozen and forgotten. If such an object exists, it would be nearly impossible to detect. It would reflect almost no sunlight and take thousands of years to complete a single orbit. Drifting past the Oort Cloud, we leave behind the last icy remnants of the solar system's material reach. Out here, beyond the scattered comets and frozen debris, the Sun is no longer the architect of motion. Its light is just another distant star, no brighter than many others in the vast cosmic ocean. But while its gravity may still cling weakly to the outermost objects, there is another force at play. A different kind of boundary, one that isn't defined by physical matter, but by the Sun's breath itself. This is the Heliosphere, the great protective bubble that shields the solar system from the true vastness of interstellar space. The Heliosphere is shaped by the solar wind, a constant stream of charged particles racing outward from the Sun at speeds of up to 900,000 miles per hour. These particles push against the interstellar medium, the thin plasma and cosmic radiation that drifts between stars, forming an enormous bubble around the solar system. Though invisible to the eye, the heliosphere is a force field, a shield that deflects harmful cosmic rays and keeps the solar system's environment relatively stable. Without it, Earth and every other world would be bombarded by high-energy particles that could strip away atmospheres and damage anything in their path. As we push outward, the solar wind begins to slow. The first major boundary we encounter is the termination shock, located somewhere around 80 to 100 astronomical units from the Sun, which means it lies about 7.4 to 9.3 billion miles away. Here, the solar wind, once moving at supersonic speeds, suddenly drops to subsonic levels as it collides with the interstellar medium. The result is turbulence, a chaotic, stormy region where solar particles slam into incoming galactic material. Beyond the termination shock lies the heliosheath, a vast, unsettled region that stretches tens of billions of miles outward. This is where the solar wind struggles to hold its ground, slowing further as it meets the increasing pressure of interstellar space. It's an area of shifting currents, magnetic interactions, and swirling particle streams, a final battleground between the Sun's influence and the vastness beyond. Then, at last, we reach the heliopause. This is the true edge of the solar system's influence, the place where the solar wind's strength is finally overpowered by the forces of interstellar space. Located around 120 astronomical units from the Sun, approximately 11 billion miles away, the heliopause is the boundary between two domains, the Sun's protective bubble and the unfiltered environment of the galaxy. Beyond this point, the solar wind ceases entirely. What remains is the raw, unaltered interstellar medium, a place where radiation from distant supernova and other cosmic events drifts freely. The shape of the heliosphere itself is still a subject of scientific debate. Some models suggest it is nearly spherical, while others propose it is elongated, like a comet, with a long trailing heliotail stretching far behind the solar system. This tail, if it exists, could extend for hundreds or even thousands of astronomical units, blending gradually into the interstellar medium. As the Sun moves through the galaxy, the heliosphere may change shape, expanding or contracting depending on the density of interstellar material it encounters. Only a handful of human-made objects have ever ventured this far. The Voyager 1 and Voyager 2 probes, launched in 1977, have crossed the heliopause, officially entering interstellar space. Voyager 1 did so in 2012, followed by Voyager 2 in 2018. Yet even out here, in the cold emptiness beyond the Sun's influence, they are still only at the very beginning of their journey. Moving at their current speeds, it will take them more than 40,000 years to reach another star system. They are alone, drifting in the endless night, carrying golden records of human culture as time capsules for any potential life that might one day find them. The Voyager probes were built for an ambitious mission, to explore the outer planets of our solar system, revealing worlds we had never seen up close before. They far exceeded their original goal, providing breathtaking images and crucial data that reshaped our understanding of Jupiter, Saturn, Uranus, and Neptune. Yet their journey did not end there. Unlike other spacecraft that eventually fall back toward the Sun or crash into their target planets, the Voyagers were given enough velocity to break free of the solar system entirely. Now, they are on a one-way trip into interstellar space, never to return. Each probe weighs about 1,592 pounds and is roughly the size of a small car, about 12 feet across, without including its antenna and instrument booms. The most distinctive feature is the 12-foot high-gain antenna, which remains pointed toward Earth, sending data at a painfully slow 160 bits per second, far slower than even the earliest dial-up internet. A trio of radioisotope thermoelectric generators provides power, fueled by plutonium-238. However, the power output diminishes over time as the plutonium decays, and by the mid-2030, the Voyagers will go silent, unable to communicate. The probes were equipped with 10 scientific instruments, including imaging cameras, which now shut down to conserve energy, magnetometers, plasma sensors, and cosmic ray detectors. These instruments helped map Jupiter's massive radiation belts, uncover the complex atmospheres of Saturn's moons, and most importantly, detect the edge of the Heliosphere, the bubble-like region dominated by the Sun's influence. In 2012, Voyager 1 crossed the heliopause, the outermost region of the Heliosphere. The probe detected a dramatic drop in solar particles and a sharp rise in cosmic rays from deep space, confirming its escape from the solar system. 6 years later, Voyager 2 followed, crossing into true interstellar space in 2018, providing additional data that confirmed what Voyager 1 had found. But beyond their scientific instruments, the Voyagers carry something even more unique: the golden records. Each probe is fitted with a gold-plated copper disc, a time capsule of human civilization. The records contain 115 images of life on Earth, from human anatomy to cityscapes, alongside natural sounds like ocean waves, wind, and animal calls. There are greetings in 55 languages, as well as a selection of music spanning cultures and time periods, from Bach to Chuck Berry's Johnny B. Good. These records are encased in aluminum covers with instructions on how to play them, and a symbolic map showing Earth's location in the galaxy. The idea was that if an alien civilization ever found the probes, they would have a glimpse into the world that created them. Carl Sagan, who led the project, called them a bottle cast into the cosmic ocean. The Voyagers are still moving outward, but where exactly are they headed? At their current speeds, Voyager 1 at about 38,000 miles per hour and Voyager 2 at about 34,000 miles per hour, they are destined to wander the galaxy for millions of years. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445, a red dwarf in the constellation Camelopardalis. Meanwhile, Voyager 2 will come within 1.7 light-years of another red dwarf, Ross 248, in the constellation Andromeda in 42,000 years. These stars are still too distant for the probes to come anywhere near them, let alone enter their planetary systems. If nothing collides with them, the Voyagers will continue drifting endlessly, long after Earth itself has changed beyond recognition. To put their journey into perspective, consider this. Even at their tremendous speeds, they would take over 17,000 years just to travel 1 light-year. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away, an unfathomable distance. If Voyager 1 were headed directly there, which it is not, it would take over 70,000 years to arrive. Despite being so far from home, the Voyagers are still providing valuable science. They have confirmed that the interstellar medium, the space between stars, is filled with a low-density plasma of charged particles. They continue to detect cosmic rays, magnetic fields, and interstellar winds, helping scientists understand what lies beyond the Sun's influence. The data they send back is precious, but time is running out. By the mid-2020s, NASA will begin shutting down their remaining instruments one by one to conserve power. By 2036, both spacecraft will likely be silent, drifting forever in darkness. By now, the Voyagers are no longer just part of the solar system. They are wanderers in the interstellar boundary, tiny machines adrift in the void, carrying the story of Earth into eternity. They are no longer bound to any world, no longer part of any system. They belong to the stars now, sailing into the unknown, never looking back. And here we are, beyond the reach of our sun, in the vast and endless ocean of interstellar space. No planets orbit here, no moons cast shadows, no rings scatter light. The forces that shape the solar system are now distant memories. This is interstellar space, the great in-between, where the sun's influence fades and the universe itself takes over. But interstellar space is not simply empty. It is a place of subtle, invisible forces, shaped by the same cosmic processes that formed galaxies, stars, and everything we know. It is filled with a thin, ghostly substance called the interstellar medium, a vast, diffuse collection of gas, dust, and cosmic rays stretching between star systems. This medium is incredibly sparse compared to the air we breathe. In the densest regions, you might find just a few atoms per cubic centimeter. Compare that to Earth's atmosphere, which contains roughly 10 billion trillion molecules per cubic centimeter. And interstellar space seems nearly void. But even these faint traces of matter hold the raw ingredients for future stars and planets. The interstellar medium is not uniform. It varies in density, temperature, and composition, depending on where you are in the galaxy. Some regions are nearly empty, filled only with wisps of hydrogen and helium drifting for millions of years. Others are dense clouds of gas and dust, where new stars are slowly taking shape. Some areas are bathed in intense radiation, blasted by the powerful winds of dying stars, while others are calm and undisturbed. Over time, all of it moves, stirred by the rotation of the galaxy and the chaotic interactions of gravity, pressure, and magnetic fields. One of the key features of interstellar space is its vast magnetic field. Unlike the magnetic fields of planets or stars, which are generated by rotating molten cores or plasma flows, the galaxy's magnetic field is woven through the interstellar medium itself. These fields are weak, millions of times weaker than Earth's magnetic field, but they play a crucial role in shaping how interstellar gas moves. They guide the flow of charged particles, influence the formation of cosmic structures, and even help direct the paths of high-energy cosmic rays traveling through the galaxy. Cosmic rays, one of the most mysterious and powerful forces in interstellar space, are high-energy particles, mostly protons and atomic nuclei, that move through space at nearly the speed of light. Some come from supernova explosions, others from distant galaxies with supermassive black holes. These particles constantly bombard interstellar space, colliding with atoms in the medium, ionizing gas, and affecting the chemistry of space itself. Despite their speed and energy, they are often deflected and slowed by magnetic fields, bouncing through space in unpredictable ways before eventually losing energy and settling into the interstellar medium. Interstellar space also carries shock waves from ancient and ongoing cosmic events. When a star dies in a supernova explosion, it sends out a blast of energy that can ripple through the interstellar medium for thousands of years, compressing gas clouds, heating up dust, and even triggering the birth of new stars. These shock waves, moving at thousands of kilometers per second, shape the structure of the galaxy itself, pushing and pulling matter into vast networks of filaments and voids. More than just empty space, the interstellar medium is a dynamic force driving stellar evolution. Over millions of years, clouds of gas and dust can collapse under their own gravity, forming new stars and planetary systems. In a sense, interstellar space is the galaxy's womb, where stars are born and eventually where they return after they die. The elements created in previous generations of stars, carbon, oxygen, nitrogen, iron, are scattered into the interstellar medium, mixing with younger clouds of gas, seeding the next generation of stellar formation. Temperature in interstellar space varies dramatically. Some regions, particularly near hot young stars or in supernova remnants, can reach thousands or even millions of degrees. But most of interstellar space is extremely cold, hovering just above absolute zero at about -455 degrees Fahrenheit. In these frigid conditions, molecules can form on the surfaces of tiny dust grains, slowly growing into complex organic compounds. Some scientists believe that the building blocks of life itself, amino acids, water molecules, and other organic materials, may have first formed in interstellar space, drifting for millions of years before being delivered to forming planets. The scale of interstellar space is almost impossible to comprehend. While distances within the solar system are measured in astronomical units of average distance between Earth and the Sun, interstellar distances are measured in light years. The distance light travels in a year, about 5.88 trillion miles. The nearest star system, Alpha Centauri, is 4.24 light-years away, or about 25 trillion miles. Even moving at the speed of the fastest spacecraft we've ever built, it would take tens of thousands of years to reach. And yet, interstellar space is more than just the distance between stars. It is the boundary, the threshold between the domain of one star and the next. Our sun's influence has faded, but ahead lies the gravitational reach of another. Alpha Centauri, the closest neighboring star system. This is where one star's reign ends and another's begins. The interstellar medium stretches between them like an invisible thread, linking them in the vast Milky Way galaxy, which itself is just one of billions in the universe. Our solar system, Alpha Centauri, and every other star we see at night all exist within this greater structure. A spiral galaxy spanning 100,000 light-years across, teeming with stars, nebulae, and countless planetary systems yet to be explored.